In this video we're going to look at how to use the Poisson distribution, which was introduced in the previous video. So, a random variable y is said to have the Poisson distribution with a parameter lambda, where lambda is a positive number, if the probability that y equals the value r is equal to lambda to the power r divided by r factorial times by e to the minus lambda, where r is any non-negative integer. That can be abbreviated to just saying y has the Poisson distribution with parameter lambda. We saw in the previous video as well that if x is the number of events that happens in a time t where the events occur randomly and independently of each other, they occur one at a time, and that on average the events occur at a uniform rate, that is, the expected number of events in a given interval is k times the length of the interval, then x can be modelled by the Poisson distribution with lambda equals k times t. It's worth having a look at what the Poisson distribution looks like, and the diagram is going to show us how the Poisson distribution with parameter lambda varies as lambda changes from 0 to 0.4 through to 15. And the major thing to notice as you watch this little mini video is that all of the time the distribution is unimodular, and that as lambda gets bigger than 10, the distribution is approximately symmetrical. So let's have a look at our first example. A fire station reports that in the area for which it is responsible there is on average 35 call-outs per week. Let y denote the number of call-outs during the next 36 hours. Suggest a probability model for y and comment critically on the assumptions that must be made for this model to be valid. And using the model, calculate the probability there will be 6 call-outs during the next 36 hours and find the probability there will be no call-outs in the next 36 hours. Well, we've got 35 call-outs per week is the same thing as saying 5 per day. So in a period of 36 hours, then we would expect 36 divided by 24, which is 1.5 days. So 5 times 1.5 is 7.5 call-outs. So the expected number of call-outs in 36 hours is 7.5. So we're going to model y by the Poisson distribution with lambda equals 7.5. Now, if that's going to be the case, then we need call-outs to happen one at a time. Well, it's possible, unlikely, but it's possible that you may have more than one incident at the same time. They need to happen independently of each other, and they need to happen at an average rate of 5 call-outs per day. Now that's implying that average rate is constant throughout the day, although it's quite likely that you're going to have more fires at one particular time of the day than you are at another time of the day. So assumptions have got to be made to use the Poisson model in this case. Find the probability there will be exactly 6 call-outs during the next 36 hours. Well, the probability that y equals 6 is going to be 7.5 to the power 6 divided by 6 factorial times by e to the minus 7.5, which turns out to be 0.1367. The probability that there will be no call-outs is 7.5 to the 0, which is 1, divided by 0 factorial, which is 1, times by e to the minus 7.5, and that gives us 0.000531. For our next example, we're told that on average there are 2.4 buttercups per square metre on Paul's lawn. And we're asked, first of all, to calculate the probability that there will be exactly 7 buttercups in an enclosed area which is a square of side 1.5 metres. So, the area of the square is 1.5 squared, which is 2.25 metres squared. So the expected number of buttercups on the square will be 2.25 times by 2.4, which is 5.4. Now, in the previous examples of Poisson distributions that we've had a time that's being considered. In this case, we've got an area that is being considered. But the argument is exactly the same. And we can say that the number of buttercups on the square can be represented by the Poisson distribution with lambda equals 5.4. Now we've got to make the usual provisos, and that is that the buttercups appear at random. They appear one at a time. In other words, you can't have 2 buttercups on the same space. And that there is this average rate of the buttercups appearing of 2.4 buttercups per square metre. If that's the case, then we've got the probability that x equals 7 will be 5.4 to the power 7 divided by 7 factorial times by e to the minus 5.4, which gives me almost exactly 0.12. Carrying on with this example, we want now the probability that there will be at least 3 but less than 8 buttercups in the enclosed area. Now, to work that out, we'd have to work out the probability of getting 3 buttercups, 4 buttercups, 5 buttercups, 6 buttercups and 7 buttercups in the enclosed area, which would be quite a lot of calculation to do. Fortunately, there is a way around it which will reduce it. So we still know that x is Poisson with lambda equals 5.4. We want the probability that x is greater than or equal to 3 but less than 8. So that's the same thing as saying that x is less than or equal to 7. Take away the probability that x is less than or equal to 2. So we want 7, 6, 5, 4, 3, but we don't want 2, 1, 0. So that's the probability x is less than or equal to 7. Take away the probability that x is less than or equal to 2. And at this stage now we can use our calculators again. So we've got a little video here showing you how to use the calculator. So first of all we go menu and 7 to select distribution, probability distributions. Scroll down to get the Poisson, then press number 3 to get Poisson cumulatives. And we want to go number 2 now, so we've got variables. So for the first probability I need x to be 7 and lambda to be 5.4. Then press equals and I get my probability of 0.8217. And then I need to do the same thing but replace the 7 by 2. And I get the probability 0.09476. So there we are, we've got our 2 probabilities there, 0.8217, take away 0.0948. So we've got the probability is 0.727. And for the third part of this question, we want to know what area of the lawn must be roped off in order to be 99% certain of having at least 1 buttercup in the enclosed area. Right, let y be the number of buttercups in an area of a meters squared. where A is chosen so that the probability that y is greater than or equal to 1 is 0.999. We can say then that y is going to have the Poisson distribution with lambda equals 2.4a. We're expecting 2.4 buttercups per square metre, so in an area of a metre squared, we'd expect 2.4 times a buttercups. Now we know that we want the probability that y is greater than or equal to 1 is equal to 0.99. In other words, 1 minus the probability that y equals 0 must be equal to 0.999. So the probability that y equals 0 must be equal to 0.001. The probability that y equals 0 is 2.4a to the 0 divided by 0 factorial times by e to the minus 2.4a. Anything to the power of 0 is 1. 0 factorial is 1. So that simplifies to e to the minus 2.4a equals 0.001. Taking the natural logarithm of each side gives me minus 2.4a equals minus 6.9078, which gives me a equals 2.88 meters squared. Next example, I've got a railway company running the trains in a region reports that serious accidents happen on average 4 times a year. Using suitable probability models, calculate the probability that, first of all, there will be exactly 3 serious accidents in the next year. Well, provided our conditions for Poisson distribution is met, we can say that the number of accidents next year will be distributed with the Poisson distribution with lambda equals 4. So, probability that x equals 3, the probability you get 3 serious accidents next year will be 4 cubed divided by 3 to factorial times by e to the minus 4, which is 0.1954. If we now consider y as the number of accidents in the next 5 years, well, we've got 4 accidents a year, so that would mean that we'd expect there to be 20 accidents in the course of the next 5 years. So y is going to be Poisson with a mean, with lambda equals 20. So we can say that the probability that y is greater than 12 is 1 minus the probability that y is less than or equal to 12. And we can use our calculator in the same way as we did in the previous example to find the probability that y is less than or equal to 12, which is 0.390. So the probability that y is bigger than 12 is going to be 0.961. For the third part of the question, if we let z equal a number of years in the next 5 when there are 3 accidents, then z is going to be binomial with n equals 5, because we're dealing with 5 years, and p equals 0.1954, because we know from part A that the probability of there being 3 accidents in a year is 0.1954. We do need to assume that the accident record of 1 year is completely independent of the accident record in other years. If that is the case, then we can say that the probability that z equals 2 is going to be 5c2 times by 0.1954 squared times by 1 minus 0.1954 cubed. And that turns out to be 0.199. On this page, there are a couple of examples for you to have a look at try and work your way through before your next lesson. So pause the video, or perhaps take a screenshot of this page. Pause the video, take a screenshot, and then have a go at these two questions and take your answers in to your next lesson.